Welcome to this lecture of the course Computational Hydraulics, and we are in module 5, flows in pressurized conduits. This is unit number 2, unsteady flow in pipes. Learning objective: at the end of this unit, students will be able to solve unsteady problems in pipes. Problem definition to solution. In this case, we will be considering one dimensional space as variable, because along pipe length there will be variation, but will not consider 2D or radial directions in our calculations. So, we will have continuity and momentum equation for our problem, and we can discretize it using finite volume approach or Godunov scheme, and resulting thing we can solve using one predictor corrector approach. So, problem statement: let us say that two reservoirs are connected. If I close a valve in between, suddenly obviously there will be change in the pressure within the pipe system, and how to model that, that can be solved using our unsteady pipe flow equations. So, variables: H as a function of H is piezometric head, H as a function of x and t, and V is the velocity, which is again function of x and t. Pressurized conduits: one dimensional unsteady flow in pipes can be represented in terms of following differential equations. So, this is A is wave speed, H is piezometric head, V is cross sectional mean velocity, and J is friction force at the pipe wall per unit mass, T is time, G is acceleration due to gravity. So, in this case we need to discretize this equation. This is in non-conservative form. Now, this equation can be written like this, which is our usual equation, and we have non-conservative form here. This means we have del H by del T, del V by del T, U as H and V. This A is V A G A square G V here. Now, this non-conservative form can be converted to conservative form with this approximation, where A bar is the average velocity or approximated velocity, A bar and bar V, and we can use this approximated conservative form for solution of unsteady flow in pipes. So, A bar is V bar here. Now, if V bar equals to 0, this is our classical water hammer equation. That means, in this case A bar will be 0 A square by G, G 0. Now, the governing equations can be discretized by finite volume method. Let us say this is our left boundary, this is my right boundary. Now, with left and right boundary I have n number of cells within my domain, and this is a typical interior cell where we have P, which is the central cell, and east side I have E and west side I have W cell, and east and west faces are there. In this case, the discretized form of the equation, our governing equation, we can write like this by transferring this f term from right to left side, left to right side, and this is our sourcing term. Now, we have discussed this Riemann problem for one dimensional conservation laws, where we are having this phi variable, which was a general variable. Now, we want to apply the same concept here. So, Riemann problem, this is our equation, and u x t, if we consider the value on the left side, this is u l. If we consider the value of this side, this is u l n. If we consider the value on the right side, this is u r. So, this continuity is there. So, this is called as Riemann problem. This is x e. So, obviously, if x is less than on this side, then we have u l, on this side we have u r. Now, eigenvalues of the matrix A bar, which is the approximated matrix there, can be calculated like this: lambda 1, lambda 2, these are V bar minus A, lambda 2 equals to V bar plus A. Applying a Rankine Hugnoid conditions across lambda 1 and lambda 2 like this, because lambda 1 is having plus value here, lambda 2 is minus value. With this condition, we can write our governing equations for a particular phase using our Riemann problem. So, what is this? On left hand side, on east side, this is my east face, whatever value is there on the left side, E minus L, this is L, this is R, V minus VL, HE minus HL, V minus VL. This is same, but lambda is multiplied here. Now, in this case, we will consider that V equals to 0 during calculation of this one. At this phase, we have a 0 value. Let us consider that, and with this calculation, we can get these two equations. Lambda 1, obviously this will be minus A, lambda 2 this will be plus A, and these values will be 0 here. So, if I apply this condition, we can get these two equations. Now, for all internal P cells, we can the following solution can be written. So, this value is directly coming from our Riemann problem. We have HL, HR, whatever value is there on the left side, right side. Based on that, we can calculate HE and HV values. Obviously, we can further simplify this with two matrices, where B equals to half 1 g by a by g, g by a like this. That means from the left side whatever value is there, from the right side whatever value is there. With this I can write the general form of the flux. Flux is AE bar at east face. That means A should be calculated at the face itself. That matrix, which is essentially a Jacobian matrix, should be calculated at face only, and this value is east face value. So, I can just multiply from my previous slide, this is AE bar into B U L n plus C U R n. So, with this information I can calculate the flux there. AE can be computed by approach 1 by setting a V equals to 0 at any phase, or by setting V bar equals to half Vp plus V, or approach 3 by setting V equals to V from Riemann's problem or Riemann's solution. For interior cell, in the first order Godunov approximation, we already know from our lectures that on the left side we will have UP, on the right side we will have this U E. So, with this information, if I calculate the numerical flux, I can simply change this subscript here. Instead of left, I am writing it as U P and right as E. So, with this I can calculate the flux at E phase. So, for flux calculation, first we need to utilize the Riemann problem solution, and we need to calculate the Jacobian matrix at the phase based on different approaches. And further what is required is specification of UL and UR. So, we can approximate UL and UR based on different schemes. In this case, for Godunov approximation, we have UL equals to UP, UR equals to UE. If we consider a left boundary, so left boundary we do not have a specific equation. So, we need to find out that thing. So, Riemann invariant associated with the negative characteristics line. So, if we consider negative characteristics line for left boundary value. So, in that case this is LB VLV, and next phase we have H res. What is this H res? In this case let us say that at the starting left boundary I have specified a reservoir head available H res. So, from this equation I can get H res minus A by G V L B equals to H 1 n minus A by G into V 1 n. So, from there I can get this VLB value. So, if I utilize this VLB value, which is H res minus H 1 n and plus A by G V 1 n divided by I have this A by G. Obviously, in this case I will get the resulting thing as no coefficient for V1 and I will get only coefficient of this one as G by A, that is this quantity there. So, in this case again I am considering that I have VLV present there. So, in that case for left boundary I need to calculate this Jacobian matrix there. So, this is VLB bar value into I have A square G, this is G, this is VLB bar. So, from there if I multiply my H res, which is known value at upstream section, because a tank or reservoir is connected. So, I have known pressure level, but velocity V LB, this quantity I can directly calculate there based on our this equation. So, remember that this VLV and VLB here there is difference. Obviously, one approximation V bar can be this one. So, I can get this flux values at interface for upstream boundary. Similarly, if we have at no advective term, or we can neglect advective term, then VLB this bar, this should be 0. And the right hand boundary again we have HRB and VRB, right hand boundary this invariant associated with the positive characteristics line. So, this can be calculated by Riemannian invariant with head with a condition. This is not directly head flow condition. From one side we have head, but other side we have if you have closure of valve. So, VLB will be 0. So, in that case where we will be having VRB as 0, we can directly get the value there. So, in this case the matrix will be our A square by G, this is constant term, we will have VRB, this is VRB, this quantity is G. Now, on the right hand boundary we know that VRB due to closure of valve we have a 0 value. If I put this 0 value here, obviously HRB on this side will be Hn n plus A by G, this Vn n. So, after multiplying this on this side I will get these terms directly. This is multiplied by G and G will cancel here. So, this is the value there on the right hand boundary. Similarly, by specifying different conditions on the boundary side, we can solve this problem. So, next part is numerical discretization and final solution. After finding out this flux values, we can update this future time level, that is n plus 1 in terms of nth level values, and the previous one was for in absence of friction, we can directly calculate like this, but if we have a friction or sourcing term on the right hand side. So, first step is without sourcing term, next second step is with sourcing term based on the first step, and final step we have this final calculation which is again with sourcing term there. So, we need to satisfy stability condition for this problem, because this is explicit approach and first order approach. So, CFL condition should be satisfied, A delta t by delta x, this should be less than equals to 1. So, with this approach you can solve unsteady state pipe flow problem with simple Riemann solution and Godunov approach. Thank you.